Okay, class, Let's get started. So we have done the syllabus walkthrough earlier. As I mentioned, that the office hour is Wednesday from 11 a.m. to 12 p.m. using the Tech Connect Zoom on Canvas. And one thing I want to clarify from the last video is that there are two types of quizzes. One is the pop quiz, which is here is stated lecture video quizzes. The pop quizzes are quizzes related to the video. So you are supposed to take these quizzes after you have seen the videos. And generally speaking, they are due on Thursday. And then there's a assignments and regular quizzes. Those are generally due on Monday. So labs and pop quizzes are due on Thursday, and regular quizzes and assignments are due on Monday. I touch upon the IDE installation and setup. We're not going to get to it in the first week or so. I'll probably do a walkthrough next week on how to install Visual Studio 2022 or above, if there's a new version coming out. And if you're interested, I have posted links on the syllabus that will guide you through how to install it and have it set up. And one thing I want to reiterate is that our assembly language for this class is on x86 CPU. So you, generally speaking, have to use Windows systems. And if you have an older Mac that is based on Intel, you can use that as well. And if you have a newer, the latest and the greatest Mac OS machine that's based on M1 and M2 CPUs, those are not x86 CPUs. And you will probably have to use the remote lab access to access a virtual machine setup in the lab. And I also posted the link for access of that on the syllabus. So this is our textbook. Okay. All right, welcome to assembly language. So most of you are probably computer science major. Some of you may be in computer engineering or interested in electrical engineering. So what are the differences between the three majors? I think the CS major is probably the best well understood. It focuses on computer programming theories, and it's mostly software related, right? It's the focus that, so when you graduate, your career path is likely to be a app developer or a system developer. Right? When I say system developer, I mean infrastructure component, such as operating system, or inside the operating system there's volume management, file system, etc. Right? Those are the system development jobs. There are those jobs probably developing operating systems for Windows and Microsoft or in Linux, or developing Linux features in Google and Facebook, etc. But majority of the CS graduate will be working in application development. Some would become, say, there are some subcategories of application development. You could be a DBA, right? a database administrator. And hardware engineering is pretty straightforward. It focuses on hardware design, right? It's CPUs, memory, chips, random access memory, RAM, and also networking. Okay. Computer engineering is really the hybrid of computer science and electrical engineering. And the focus is on the interactions, communications between hardware and software, right? And, graduate of computer engineering people can work in software development. Not so much for electrical engineering grads, right? But computer engineering can go either software or hardware after they graduate, or they can work in system integration, making, the, different systems, computing, networking, storage that work together. Ultimately, the reason we all use computer, use our phone, is because the applications. We want to use the applications. And all these majors, at the end of the day, they are all kind of build things so that people can run apps. Computer science perhaps is the closest to applications. But it cannot be done without the supporting part of the computer engineering and electrical engineering part of the what I call the application stack. Well, what would you learn in this course? You are going to learn basic principles of computer architecture on using x86 processors. And you're going to learn how data representation is done, right? We all heard about everything at the machine level is either zeros or ones, right? How do we use zeros and ones to represent numbers, characters, etc., right? And instructions, etc. And you're going to learn Boolean algebra and digital logic and computer organization, how computer is organized at the hardware level and at the operating system level. Not necessarily in depth, right? Because each of these topics is a really big topic. So we are not going to get super deep into computer organization, but enough that to give you a good understanding to allow you to feel comfortable writing assembly code. And then you learn elements of assembly language, the basic instructions, instructions meaning the machine instructions. Branching and looping, how to do branching and looping using assembly code. And you guys have taken C++, and branching just means if then else. Looping is for loop and while loop, etc. And procedures. Procedure is a block of code that you can call it right over and over again. It's a little bit similar to functions or methods, but it's not as sophisticated as functions or methods in C++. But it's a little bit similar. And you're going to learn bit manipulation. Actually, this is a pretty interesting topic, how you manipulate bits to do mathematical calculations. And you're going to learn how to do string operations and for math, how to do floating point operations that would do calculations on non-integer numbers. So, let's see. As I mentioned before, assembly language for x86 processors focuses on programming microprocessors compatible with Intel and AMD. And really, there are only two manufacturers, Intel or AMD, that's building x86 processors. While Intel is the company that first created the x86 processors in the 1980s. Later on, Advanced Micro Devices, AMD, saw this as a very lucrative business, and they sort of reverse engineer the instruction set of the x86 processor from Intel. And yes, there was a lawsuit, and ultimately AMD prevailed because they did not steal any intellectual property. All they did is reverse engineering, which is permissible. So right now, these two companies, the processors that they produce are completely compatible, right? And you can have Windows running on AMD machine or an Intel machine. They behave the same. So for CPUs, for assembly code, if assembly code runs on Intel, it will run on AMD. Okay. And the next concept I'm going to introduce is an assembler. An assembler is basically a program that converts source code program from assembly language into machine language. Assembly language, as you will learn later, is actually a user-readable language. Right? It uses characters, symbols. You can make sense of it. Machine language, on the other hand, is all zeros and ones, and is completely not readable by human. But the CPU does not understand assembly code. It will understand machine language. The Microsoft Macro Assembler, also known as MASM, is included in most versions of Microsoft Visual Studios. And that's what we're going to use for this class. And there are other widely used assemblers for x86 systems as well. And we're not going to learn any of those. Now, you may use the NASM assembler on Mac. I think it is MASM. For older Intel-based machine only. There's a typo there. I'm going to fix it before I upload this PowerPoint. Now, you may ask, is assembly language portable? Now, some of you may not even know what portable means. Portable meaning that when you write a program, it can run on many platforms, run on many computer systems. And if you have learned about Java before, Java language is designed that you write the code, you compile the code into something called bytecode, which will run on any Java virtual machine running on any system, right? It could be a thermostat system, it could be Mac OS, it could be Windows, it could be Linux. These Java machines will run the Java code that you write for on one platform, and it's going to run on any other platforms. So that's called portability, meaning you can move the program from one type of computer to another type of computer. It will run just fine. It's called portable. Is assembly language portable? No, it is not. Assembly language, for example, only runs on one system. Right? For the x86 assembly code, it only runs on x86 machines and nothing else. There are other well-known processor families. Motorola used to make 6800. That processor was used by early Macintosh computers. In fact, I think it was used by the first Apple computers. And you have Intel x86, you have Sun Microsystems SPARC, and VAX, which is part of Digital. They no longer exist. IBM 370 is a mainframe computer. It's still widely deployed today, and it has its own assembly language. And then there are newer design of CPUs called ARM, and this is a whole family of CPUs. Apple makes its own ARM style chips. Apple calls it M1, M2, and I suppose moving forward, the next generation is going to be M3. And now Apple is going to use that to replace x86. Windows and Linux these days are still mostly, I think the vast majority of Windows and Linux are running on x86. x86 is proven to be very capable, really inexpensive, and very reliable. And there are downsides of that compared to the ARM style chips. ARM style chips is more energy efficient, and it is faster in running many workloads. But if you are going to take a look at the current state, what family of CPUs are the most widely deployed, widely used? That would be x86. The instructions in assembly language may directly match the computer architecture, meaning that when you run the machine code, and the instruction will translate into hardware action. So basically, the CPU hardware itself is going to be able to interpret the machine code, and then use hardware features to do the executions. And there are some architecture that may require another layer of translation called a microcode interpreter. And basically what that means is that the machine code generated by the assembler, all the instructions in the machine code are not supported by the hardware. So you have to sort of go through another translation to another layer of machine code, so that the hardware, the CPU can understand, can execute the instructions. Now, how does assembly language relate to machine language? So machine language it's a numeric language, zeros and ones, and it's only understood by a computer's processor, right? So all x86 processors understands a common machine language. Assembly language, as I mentioned earlier, uses short mnemonics such as ADD for add, MOV for move, SUB for subtract, and call for calling a procedure. Right. So that's sort of human readable. Assembly language has a one-to-one relationship with machine language, meaning one lines of assembly language code will directly correlate to one lines of machine language code. Okay, so you can look at the example underneath, and on the left is the machine code represented by hexadecimal numbers, and we're going to talk about hexadecimal numbers this week. And they map to basically zeros and ones, right? Binary numbers. And if you can read the left, it's completely not readable, right? And the line of code on the left correlate to the line of code on the right, MOVEAX 5. What that means is that you're going to copy a number 5, into a registered, which is a very fast memory. We're going to talk about that later, what registers are. You're going to copy number 5 to register EAX. Okay? And then you are going to add the number 6 to whatever number it's in the register EAX. So of course, assembly code is readable. Now, compared to C++ or Java or Python, it's not as natural. But nonetheless, it is human readable. Now compare that to a high-level language like C++ and Java, how they relate to assembly code. As I mentioned earlier, assembly code and machine code have a one-to-one relationship. High-level languages like C++ or Java, they have one-to-many relationship, because these languages are a lot more natural, they're a lot more human-like, and it's further away from the language the machine can understand. So each line of code in C++ or Java often correlate to many lines of assembly code. Okay, let's take a look at an example, right? This is a C or C++ code. It's the same syntax. You declare an integer y, you initialize its value to 3. And then you add number 4 to y and multiply the result by 3. And then you store the result in a integer variable x. Now, when you write this code, you don't care about memory, right? Where to store temporary values and things like that. It is relatively user-friendly, right? Easy to understand, easy to write. Now, when you translate that into assembly code, these 2 lines of C or C++ code correlate to 5 lines of assembly code. So it involved with this. First, you store the value of that's in variable y to register x, which is a fast memory available inside the CPU. And then you add 4 to that register. Okay? And then you move another number 3, to another register, EBX. And then you do an integer multiply, EBX. And it will multiply what is the result of the y plus 4. And then you are going to take the result of EAX and copy that to X. Now, all these may make very little sense to you right now. So the takeaway is that 2 lines of C or C++ code correlate to many lines of assembly code. So let's compare to assembly language to high-level languages, and where it's best to use what language. Okay, so if you're building a commercial or scientific applications, right? You write it for a let's say a single platform. Let's say run on Windows. And the size of it is medium to large. What language to pick? Obviously, you are not going to pick assembly language because you're talking about a medium to large size applications that could be in, hundreds of thousands of lines of code. And to write a sizable program like that using assembly language, it's just not feasible, right? And it's possible, but it's not very feasible because it takes probably years of effort, right? So the language of choice is usually a high-level language. And it could be C++, it could be Python, it could be Java. Right? What about a hardware device driver, like a let's say a printer, right? You buy a printer, you hook it up to your machine, or you connect it to your machine through the network. And in order for your PC to recognize the printer, right, it needs to run the device driver for that printer. And device drivers are usually pretty small. devices like printers or USB drives or things like that, and they usually don't have a lot of memory set aside to run code. So the language of choice is often assembly language because it doesn't take a lot of resources to run, and it's extremely fast. And you don't care about its portability, right? It's written for a very specific piece of hardware. And moreover, one important thing to keep in mind is that assembly language, you are dealing with hardware features directly, and you can take advantage of various hardware specific features. And high-level language do not, right? Like we saw earlier, high-level language, we don't, when you do the, multiplications or additions, you don't necessarily need to know how the CPU step by step do the calculation using registers, right? And there are certain things it's best written in assembly language because it can allow you to take advantage of hardware features. Okay, now for commercial or scientific applications written for multiple platforms, and for that kind of applications, obviously assembly language is out, right? Assembly language is not portable. That means that if you want your user to be able to run the application on different platforms, right? If you have Instagram, you want Instagram to be able to run on iOS and also Android, and also on the browser on the desktop. But you don't want to rewrite the app for every single platform, right? So I think you probably use a more high-level language like Java or Python, and to write that kind of applications that's portable. And then you have the last type of application we are looking at is embedded systems and computer games requiring direct hardware access. Okay, so embedded systems, we all know about gaming, right? Gaming system, inside your gaming console, there are various subsystems. These subsystems, they don't, if it's a PS5, it doesn't care. It's going to run on, Xbox or not. It only cares about it runs on, Sony workstation. So, for things like that, you want really high performance. You probably want to run pieces of it at least using assembly code. Now, the other type of embedded system is so-called real-time system. Let's say this is happening right now. Let's say Russia sends a missile to Ukraine, and Ukrainian defense will try to intercept the missile. And the intercept missile needs to react in a real-time fashion. And it runs a embedded system, and this system require you to react really, really quickly. And for that type of system, the ideal language is usually assembly language. So that concludes this video.